Okay, we're going to start. We're going to finish up 2.2 with one new idea. So 2.2 continues. Let's talk about the idea of continuity. So the idea of being continuous or being a continuous function. Intuitively, this is the property being able to sketch a function without lifting your pencil off the page, or whatever you're drawing with. Right, and so this basically says that, you know, the function has no gaps, no holes, nothing that otherwise impedes you sketching the function in one fluid motion. Okay? But that definition only is very good intuitively, because there are a lot of functions where, while in theory we can sketch them, it's not something we'll ever want to have to do. But that would be the idea. Something where your function is just continuously moving on and there's no jumps, no gaps, no holes, nothing fragmented. We say a function that has this property is continuous, right? Or it's continuous on the interval where it possesses these properties. So continuous functions might be, you know, they might look like functions you've seen before. So, for example, that guy is like a continuous function between A and B, because it keeps moving. I didn't have to lift the chalk off the board to actually finish drawing that function, so that's an example of a continuous function. Whereas something that's not continuous, it can be not continuous in various ways, right? So one, it could be, I'm drawing this function, but there's a hole here that I have to lift up my pencil off the page to avoid. Right, so there's like that, it could be discontinuous. It could also be discontinuous in the sense that I have to stop somewhere and make a jump to somewhere else. Right, so that's like another reason why it can be discontinuous. Or maybe I have to jump to the side over somewhere, and that's a discontinuous function. So then in this case, I shaded this in here. But it's also possible that function at a certain point might have a different definition other than what it's normally doing, which is not entirely strange to do. So these are all examples of something that's not continuous in some interval, right? It's not, you can't draw it in one fluid motion, you have to make a jump or you have to avoid a hole or something like that. And so the property of not having to do any of these things is called being continuous, or having continuity, or being a continuous function. And it's important to be able to do these because it turns out that we can only do calculus on a part of a function that is continuous. So it's important to know when something is continuous from when it's not. And it turns out we can use limits to determine when a function does possess this property. So leads us to our first definition for this today. We say f of x is continuous at a point x equals a, right? So I pick some x value and I want to talk about what does it mean for the function to be continuous at that point. If the following holds, if the limit as x approaches a of the function is actually equal to the value of the function at a. So if I evaluate the function at a, I will get a number. If my limit actually equals that same number, then the function is called continuous at the point x equals a. Now it turns out if that equation is fulfilled, none of these bad things that I mentioned over here will actually happen. Making sure that that equation is fulfilled prevents all gaps, all holes, all jumps. They will never happen in this case. Note that three things have to happen here. And taken all together, it kind of forces you to be able to draw that function without lifting your pencil off the page. 1. F of x must be defined at the point. Right? So it has to be true that you can actually compute this value f of a. Right? So that gets rid of the fact that there is a hole at that point that you can't fill in. You should always be able to fill in the hole. So this must always make sense. It should always be defined at the point a. The second thing is that the limit as you approach a of f of x must exist. Right? Which, by the way, that also means that as you're approaching from the left, it must exist. And as you're approaching from the right, it must exist, and they must be equal. So the function must be defined at the point, the hole needs to be filled in wherever you're at the point, and the limit must exist at the point, meaning as you're approaching that point, you must be able to get a y value output. Thirdly, what needs to happen is that these two things have to agree on what their answers are. 1 must be equal to 2. Right? That is, the value that the function is defined at the point must actually be equal to the limit as we're approaching that point. So these are the three things that need to happen in order for this equation to be fulfilled. And it turns out, if these three things happen, your function is continuous. You can draw it without lifting your pencil off the page. So let's actually look at some examples. But this is the important part. And I probably asked this as a bonus on the test. I don't remember. I asked you several equations. But I asked at some point on either a quiz or a test to use an equation to define when a function is continuous at a point, and this would have been the answer that you wrote down. So it's when the limit as you approach the point of the function is equal to the value of the function at that point. And in order for that to work, the limit has to exist, which means each one-sided limit needs to exist, and the function needs to be defined at the point, and those two things must be equal. They must be the same value. I did break this up into several examples, but maybe I can just do one big example. Let's just do one big example. Kind of cover all these situations. So I'm going to give you the example in a graph, but of course the example doesn't have to be a graph. It could be like a piecewise defined function or something similar. the blue is not a part of the graph, it's just so that you can see what the numbers are. This one, 10 minus 8, so minus 5. This is obviously at 0. 2. This is 1, this is 2, that's 3. So this is the example of one big function f of x. It's doing its thing, that's what it's doing. And we're going to examine it at all these blue points that I mentioned here to determine whether it's continuous or not. Now on the graph you should be able to tell whether it's continuous or not there. What do you think about at minus 10?
Not continuous.
Not continuous. Why? There's a hole. You have to lift up your pencil off the page to avoid that hole. What about 8?
Not continuous.
It's not continuous there again. Again, you have to lift up the point, you have to fill in that point, and then you have to continue. What about at minus 5? There's a whole gap. There's an asymptote that you have to avoid, not continuous. What about 0? Yeah, I could literally draw through 0 at that point and not have to lift my pencil off the page. Obviously at 2 that doesn't happen. At 5 that's actually okay. I just go up and then come back down. Didn't have to lift my pencil off the page. 8 is a problem. 9 is actually a problem as well because notice that there is no function here. I can't actually just draw through that point without lifting my pencil off the page. And 10 itself has a gap. But, let's actually fill that in. So we can kind of see from the picture what's going on. But let's actually do it mathematically, just in case I didn't actually give you a picture, but rather I gave you like a piecewise equation where all of these pieces, when you actually graph them, this is what you would have gotten. So let's look at here, x equals minus 10. Let's examine some of the main numbers here. So let's look at the limit as x approaches minus 10 from the left, as x approaches minus 10 from the right. What does that mean as x approaches minus 10 overall of our function? And what is f of minus 10? And then from that we'd be able to say whether it's continuous or not. What is the limit as I approach minus 10 from the left?
1.
It's 1. What about from the right?
1.
It's also 1. So what is the limit?
1.
The limit actually exists and the limit is 1. What is this?
Undefined.
Undefined. So you see, just by the numbers alone, I can see that my limit is existing, it's giving me number 1, but my function is undefined at minus 10. This means it's not continuous. You could do the same thing at minus 8. Let's look at what would happen here. Let's talk about the limit as I approach minus 8 from the left, limit as I approach minus 8 from the right, limit as I approach minus 8. And let's talk about the function evaluated at minus 8. What happens here?
2.
That's 2. So from the right you get 2 again, so the limit does exist and the limit is 2. What is the value of the function at minus 8?
3.
The value of the function is filled in here, that's actually 3. So here, all these guys give me a number, they give me an answer, but these two, the limit is not equal to the value of the function at the point, therefore it's not continuous at the point, because it means I would have to lift my pencil up to go fill in the point at 3 before coming back down at the level of 2 and continuing. So again, not continuous. If you look at 5 at x equals minus 5, you can do the same sort of analysis. Look at the limit as x approaches minus 5 from the left of f of x. And this would be negative infinity, bless you. And this, if you look at the limit as negative 5 from the right of f of x, it's also negative infinity, which means overall the limit here as we approach minus 5 of f will be negative infinity, but f of minus 5 is undefined. And so that's not continuous. We can talk about it at x equals 0. Limit as x approaches 0 from the left of our function is 2. Limit as x approaches 0 from the right of our function is 2, which means that the limit as x approaches 0 of our function is 2. And if I look at f of 0, that actually gives me the number 2 as well. So here it is continuous. I can draw my pencil through without lifting it up. Let's go through the motions here for 2. Notice here that the limit as x approaches 2 from the left is actually 2, while the limit as x approaches 2 from the right is actually 1. So the limit as x approaches 2 of our function does not exist. So that automatically means it's not going to be continuous because the limit doesn't even exist. Our function, it is defined at 2, it's defined to be 1, but at the end of the day it's not continuous. And I think we're getting the idea here. So let's not actually go through this anymore. This guy here, you have no right-hand limit. This means limit does not exist, which obviously means it's not continuous. This guy has no left-hand limit, so the same reason applies. No left-hand limit. So it's not continuous. This guy, well, the same reason as 8, no right-hand limit. There is such a thing as one-sided continuity, but we're not going to concern ourselves too much here. So technically 9, we could say it's continuous if we're coming from the right, but it's not continuous as we're coming from the left. But that's not something we care about. So I just care about continuities in general. So that's an example of can do with continuity. It's just checking the numbers, making sure they all have to agree. Whether you're taking a limit or you're evaluating the function, all the numbers have to line up. Like here, we got 2, 2, 2, 2, 2s for everybody. Or whenever that happens, we're continuous at the point. If any one of these guys mess up, we're not continuous at the point. We can also talk about continuity in general. We say f of x is continuous. If, right, so before we talked about continuous at a point, here I'm just talking about continuous in general. But this is just basically us taking that definition and applying it to all points of f. So if you apply that definition about continuity with limits, but you apply it to every single point in a domain and it always checks out, we say the function is continuous in general. So there are a bunch of examples of functions that are continuous in general. These guys are continuous on their domains. And it's kind of the functions that we already like. So polynomials have this property. You'll always be able to find the limits and match them up with the value of the function at any given point. Radicals have this property. As long as you're in the domain of the radical, you will be able to do this. Rational functions have this property. As long as you're not divided by 0, you will be able to make that limit equation work out. Exponentials and log functions do this. So these are all functions that are continuous on their domain. As long as you're in the domain of the function, the limits will always match very nicely with whatever the function is doing at the time. Now, continuity is important, as I mentioned before. Because we can only do calculus where we are continuous. Calculus does not work in the gap, it does not work on jumps, it does not work if there's a break in our function, calculus will break down as well. So it's important to know when our function is continuous and what kind of functions we can kind of do calculus on without worrying about it really. Because we can only do calculus where functions are continuous. I will mention here, and I will give you examples later, continuity doesn't guarantee this though. I will be giving examples of functions that are continuous, but calculus still will not work. And then we'll talk about why it will not work. But not being continuous definitely guarantees that you can't. And so with that, we end section 2.2. Kind of the last thing I wanted to really talk about, the last new idea, the idea of continuity. Although I did some limit examples with my other classes, I probably want to see how you guys deal with them. It might come up in the homework, so it'll probably be nice if you can look at it. So let's look at some more limit practice problems. And tell me what you would do with something like this.
Would you allowed to use calculator?
Huh?
Would you allowed to use calculator?
No. I mean, a scientific calculator wouldn't be able to do a limit anyway. Graphing calculators aren't allowed. So that is something you'll have to kind of work out. About limit as x approaches 0. Okay, so what are your ideas here?
Table of values.
Table of values. So if you're on like a quiz, you'd want to do a table of values for that guy? Would that be annoying?
I mean, I would do like 1, 10, 100 in both directions quickly. Probably knowing what the square root of.
You mean you try to plug in like x equals 1/10 and then 1/100?
Ooh, no. Like whole numbers.
You're approaching 0 though.
Oh,
Remember, if you're doing the table of values, the goal is you have to actually be approaching that 0 number.
Yeah, but it's like going backwards. If you count down from like 100, then 10, then 1, you're still getting closer to 0.
Yeah, but not in terms of how a limit gets close to 0. When you're talking about limits, you want to get super close to 0. I mean, being at 1 is considered very far away. You really want to be like 0.1, 0.01, 0.001. You really want to be close. Like, limits really approach very, very close. Right, talking about approaching from like 100 and then 10 and then 1, it's not what limits are about. Limits are about getting infinitesimally close to something, like approaching something with like asymptotically. That's how limits apply. So if you're going to do a table of values here, the values you'll be plugging in is things like what I was saying, like 0.1, 0.01, 0.001, 0.001, 0.00001. You plug in a bunch of those numbers. That doesn't seem like a fun time to. Any other ideas? Yeah?
You can put the rad 4 plus x in the parentheses and raise to the 1/2 power. So you would like know different degrees.
Okay, but what would you do after that point?
Conjugate complex.
Huh?
The conjugate complex then?
The conjugate. We could actually do a conjugate. We've actually simplified things like this before, where we can do the conjugate. So we can actually just multiply and divide by the conjugate of this guy to try to simplify, because if you can't, obviously we couldn't plug in x equals 0 right away. So the next thing we might want to do is see if we can simplify to plug in 0. Simplifying something like this we've looked at before, it's actually multiplying it by the conjugate. So we multiply by 4 plus x plus 2 divided by 4 plus x plus 2. So now on the top, we're going to multiply these two sets of parentheses. Notice here that what we have is something that looks like a minus b times a plus b. So when we multiply those, we get a squared minus b squared. So that's what the numerator becomes. The denominator is just going to be x times this whole thing. The numerator we can now simplify a little bit, because that's a 4 minus a 4. So we end up with here x over x times this guy. Now the x's can cancel, so now we can cancel that x in the denominator. Let's limit that at x approaches 0 of the radical of 4 plus x plus 2. And so now I can plug in x equals 0. That will give me radical 4, which is 2. And I add another 2, so that's 4 in the denominator, so this just becomes 1/4. So sometimes these limit problems, they do require some sophisticated kind of simplification, but it should be things that we've seen before. So in this case, multiplying and dividing by the conjugate would be the way to go. Similarly, we can look at something like this guy. And obviously, again, we cannot plug in x equals 0 because we divide by 0. So you want to do some sort of simplification process here. And because it's a complex fraction, it's a fraction with fractions in it, I multiply and divide by the LCD. So the denominator of that is 1, the denominator of this is 1, the denominator of that guy is x plus 1, so x plus 1 is the LCD. I multiply and divide by x plus 1. This is how I deal with this guy. So now this is going to distribute, multiply this, multiply that. So I take x plus 1 times 1 over x plus 1, the x plus 1's cancel, I'm just left with 1, minus 1 times x plus 1, that goes in parentheses, and then the denominator I add x times x plus 1. I'll simplify a little bit, 1 minus 1, we'll kill that guy, I'll have a negative x left over in the numerator. And the denominator is going to be this. So now I can cancel the x's. So that's the limit as x approaches 0 of minus 1 over x plus 1. In which case now I can plug in 0 for x because the denominator is no longer 0. So I get -1 as the answer. I think now we can be finished with 2.2. Just show you. I just wanted to show you a little bit more complicated examples of limits. But now with that out of the way, we can actually start to do something very important. This is where our semester is going to take a turn for the better. Do a lot more interesting mathematics now. So this is 2.3. I'll kind of couple it and do 2.4 at the same time, where we're going to talk about the derivative. And I'll mention some of its applications, although we'll do more applications in further sections. So we're going to talk about the derivative and its applications. So I mentioned this before to you about what calculus is about. If you have to say, what is calculus the study of? The one-word answer would be limits, and we're going to see why. But the longer answer would be, it's about derivatives, integrals, and their applications. So we're going to look at one of those guys today, the derivative. The integral we'll look at towards the end of the semester. So, but for now, we're going to look at the derivative. So here's what that's about. There were two major kinds of problems that mankind needed to be able to solve early on. One of these were the fact that in life, you just look around at everything around you, you realize things are constantly changing. You know, volcanoes are erupting, you know, things break down and decay, populations grow, you know, radioactive elements dwindle. You know, things are constantly changing. You know, the grass in the field would grow, and you know, things are moving all the time. And sometimes when we need to actually plan for something in the future, or make a prediction, or somehow come up with rules or laws that would govern certain things, we want to figure out how fast things are moving, how fast things are changing, so that we can know, okay, if we're right here right now and I realize it's growing this fast and I kind of expect it to continue doing that, what is it going to mean 10 years down the road, 5 years down the road? What is it going to mean in the future? How can we actually capture this idea of figuring out how fast something is actually moving, you know? And some things are actually easier to do. Like we spoke about linear and exponentials, for example, and we can realize, oh, we can measure something with a linear function if I realize it's adding the same fixed amount every unit time. Or something we can measure as an exponential where it's adding a fixed percentage amount per unit time. But what if we see something growing and it's growing in this weird way and you can't really see a pattern? How do you put a function on top of that, right? That kind of becomes very complicated. So finding out how fast something is growing or decaying is a very important problem. And that was referred to as the rate problem. And it turns out that the mathematician's answer to that problem is the derivative. The derivative is going to be that guy that we can figure out the rate of change for things that seem random and haphazard. We can actually put a mathematical structure on top of them that can study that motion and actually come up with some concrete answers. The other kind of problem that we needed to solve was the so-called area problem, figuring out how much space something takes up. So sure, the area of a rectangle is something that we all know about, but what if you're a farmer and you own a plot of land with this weird shape? How do you know how much land you actually own, right? That might be important. You might want to know how many crops you can plant, or you want to know that the government isn't trying to overtax you on land and asserting that you own more land than you actually own. The idea of how much space something takes up is also very important. And so people have been studying these problems individually. They're talking about figuring out how fast something is moving and how much space something is taking up. And we got pretty sophisticated on these things pretty early on. Like Archimedes, for example, who lived in the 200 BCs, he could figure out how much space random things take up. And he was very sophisticated, believe it or not, when you come to that. But then, when it came to the time of Isaac Newton, it turns out that the rate problem and the area problem were actually connected in some strange way. And that's what Newton and Leibniz figured out. And that's kind of why we know them as the fathers of calculus. It's not because we never knew about calculus until they came along. Human beings have been doing calculus for thousands of years before these guys. But these were the two guys who kind of realized, hey, there's kind of a connection. There are these two problems that we need to solve in the world. But they're really two sides of the same coin. And they developed an entire theory around that, and that theory became calculus. So it's a theory of calculus. This is a theory of trying to solve the rate problem and the area problem, and noticing that these two guys are actually two sides of the same coin. And that's what gave rise to calculus. And so now we're actually going to study one of those guys. We're going to talk about the derivative. We'll talk about his connection to the other guy, which is the integral. That guy used to solve the area problem. And we'll kind of end the semester there by the time we get to that point. So we're going to spend a lot of time on the derivative and what it can tell us. The majority of the rest of the semester is going to be us playing around with this guy. But he's the solution to the rate problem, figuring out how fast something is moving. So we'll start this section with the goal in mind, that we want to measure rate of change. This is the point. We see things changing all the time. We want to know how fast they're changing. What is the rate of change? And we want to do so. The phrase is called instantaneously. So the goal here, spell that correctly, instantaneously. Right? Because we do know one rate of change, right? We know about average rate of change. So that was when we were changing over some interval, and we could actually measure that with the slope of a line and figure out how things are changing. But that you kind of have to know about these 2 points and kind of look at them in hindsight and know what values the function is going to be at some point in the future. But you might not have that. The idea is, what about at this point? Let's say I don't move into the future, but I know that I just want to know what is the rate of change at this point. How would I do that? Right? That's what we're having. We want to figure out. How fast is something changing at an instant, at a single point, right? Not over some time on average. Right now, in this moment. How fast is it moving? And what can that tell us about the very next moment? Right? So that's the goal. We want to be able to do that. So here's some things that we know. So we know about average rate of change. We also know, we mentioned this before, the slope of a line can be a measure of rate of change. The goal is we're going to combine these ideas. To cover more complicated cases. Which is, that's kind of one of the main things you do in mathematics. You figure out the solution to a simple problem, and then you kind of tweak that solution to deal with more complicated problems. You might have done that in geometry, for example, where basically you figured out the area of a rectangle, and then you're like, okay, we can use that to figure out the area of a parallelogram, and then we can use that to figure out the area of a triangle. And so when we come to something like a circle and want to figure out the area of a circle, what do? We actually slice it up into a bunch of piece of slices. We can say each of these piece of slices is like a triangle. We stack these triangles together to get a parallelogram, and then we use the parallelogram formula and we pop out with pi r squared. Right? So to get to a more complicated answer, we can use things that we already know about, things that deal with simpler cases, and we're going to kind of build on that. So that's what we're going to do here. So far we know these two ideas, and we're going to actually use those ideas to come up with a way to measure instantaneous rate of change. And so here's how that's going to look. So here's the idea. I have my function, it's doing its thing, that's your f of x. And let's say I care about here. I want to be able to draw a line there. That's a very convenient kind of line. I'll talk more about what this line is. This guy here, he's called a tangent line. So the idea is how we're going to combine this is because we know how to measure a rate of change for the slope of a line, we can kind of, if we care about how fast a function is changing at a certain point, what I want to do is be able to draw a straight line that passes through that point that has the property that if I zoom in far enough, the difference between the line and my function is negligible. And so by measuring the slope of the line, it's kind of like me measuring what the function is doing as well. So this is a tangent line, and the idea is that if you zoomed in, the function, the other one, function and the line are super close to each other. You can zoom in and they're kind of like it's the same thing. And the closer you zoom in, the closer together these things seem. And so how we can get to that line is we can start with the average rate of change. So I pick another random point at some point in the future. So let's say I care about the point x. I can pick another random point at some point in the future, say x plus h. That's a distance h units away. And I start by connecting a line that connects through those 2 points. That line is called a secant line, by the way, so you might see that in your... So a secant line is a line that connects 2 points on a curve. A tangent line is a line that passes through a curve in one point that approximate the curves at that point. If you can, that means if you zoom in, they'll kind of, the line and the curve would do the same thing. So you can start by there. Now the idea that you want to, the idea is we want to change the secant line into the tangent line. And we can do that by kind of fixing this point and pushing this point towards that one. And you realize that the closer you make that point to go to here, the more that line becomes the tangent line. Eventually you'll push that point up beside this point so much that there's no space between the two. Where drawing the line between the 2 points is kind of like drawing the line between 1 point, right? So in other words, what you're doing is you're closing the distance between these 2 x values. You're essentially letting this h value go to nothing. And now the question is, do we actually have a mechanism to do something like that? To actually let our h value approach a certain number? What could we use to do that? A limit, right? That's all that limits are about, is to close some distance, is to approach something and get super, super close and zoom in super, super far. And so that's what we can do. Here we can use limits. And we do this so that the secant line becomes a tangent line. So let's actually figure that out. Like, what would that actually look like if we did that? So we can imagine here, if we have our function doing this thing, that's f of x. Here this is x plus h, which means that this guy here is f of x plus h. This guy, the y value here is f of x. I can use a line that connects these 2 points, so I can end up with what's called the slope of the secant line. And that's going to be y2 minus y1 over x2 minus x1. We're going to get that f of x plus h minus f of x all over h. And so this means now that the slope of our tangent line is simply going to be what happens when we let this distance h go to 0. So what we're going to do is, from that expression, we're going to take a limit as h approaches 0 of this expression and that will end up being the slope of a tangent line. And again, that's the expression we've been seeing all the time. That's the difference quotient. But now we're taking a limit as the denominator goes to 0, which is kind of why I told you guys in the beginning that when you're simplifying something like this, the goal is always to simplify it to a point where you cancel that h in the denominator. And the reason is because we are going to eventually want to plug in h equals 0. So this guy, this is an important expression. It gives us the slope of a tangent line, which is going to have a lot of nice properties. And we give it a name. Because it's so important, we're going to name it. We're going to call it something because we're going to want to refer to it all the time. And the name of this expression, you might have guessed it, is called the derivative. So this brings us to the definition here. The derivative of a function y equals f of x at x is given by that limit. The limit that's it's equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. It's a very important expression. We call this guy the derivative of the function. Provided it exists. I mean, it's the limit after all, so it's possible for limits to not exist. If such a limit exists, though, it creates for us a new function, which we will denote using this notation, f with an apostrophe. Right, that's called a prime notation. That was actually the notation that Newton developed. But this expression will give you another function which you can think of as the slope of the tangent line. So that's going to be an expression that gives you the slope of the tangent line. This is useful since the tangent line approximates the function at the point. So the rate of change of the tangent line is effectively the rate of change of the function that we drew the tangent line to. Now we know how to measure the rate of change of a straight line, we just did that using the slope. So now we're using something that we know how to compute, but we're applying it to some other random function. Right, so as long as this limit exists, we give it the name the derivative, and it is a function. Because when I compute this limit, I'll actually get another function, which I call f prime, or the derivative of f, and that's what it gives me. It tells me about the tangent line to the function. Let's talk a little bit more about this notation, but you need to box this because you need to have that memorized. So if I ask you to define the derivative using limits, or use the limit definition to compute a derivative, this is what I expect you to be using. How about notation? The one is f prime of x. Or I might write f prime when it's understood. We'll only have one variable to worry about at any given time here. So you can just write f prime. This is red f prime. Or f prime of x. It's actually the derivative of f with respect to x. It's also the slope of the tangent line. To f at x. You can also think of it as the rate of change of the function. That is how fast f is changing. Right, there are many interpretations to this guy, but you do want to know that, be able to think of it as the slope of a line, but the slope is also a measure of rate of change. And so you have this notation, which is called a prime notation, because this guy here is called a prime. That's one of the major notations. There are many notations for derivatives, but there are really only two that we're going to see often in this class. For the most part, if I'm writing something on the board, I'll write that notation because it's less cumbersome than this other notation I'm going to give you. But there are good reasons to have this notation as well. This is called the Leibniz notation. It turns out that Newton developed a theory of calculus, but another mathematician developed a theory of calculus independently. And his name was Gottfried Leibniz. And he came up with another notation for the derivative. So it's called the dy dx. So we call it dy dx. Or you can think of it as the derivative of y with respect to x. So you might see this notation. You could also see something like df dx. But usually we would say something like dy dx. And of course, the variables here, like x and y, it really depends on what variables I'm using in the problem. So if I call my function p and my input is t, I can talk about dp dt, or I can talk about p prime. Right? So these are two of the main notations. This one is really nice because it's a very functional notation. You can actually treat it like a fraction. You can treat a fraction a lot of times, so you can multiply both sides by dx, you can flip it and move stuff. And so there are times when this guy is very useful. But either notation here is going to be applicable in this class. And I'll mostly be using this one just because it's easier to write f prime than to write dy divided by dx. So it's just me being lazy. Okay? Let's actually do an example. But another thing is, it's very important of you being able to interpret what this gives you. Okay, so it gives you the slope of the tangent line to the function at the point, which also talks about the rate of change of the function at the point. So let's do an example. Find the derivative of say y equals f of x equals x squared at the point x equals 2. And interpret your answer. Let's actually do that. Here we know the derivative. This is just equal to f prime. My f prime is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That's limit as h approaches 0. What is my f of x plus h for this function?
Plus h squared.
X plus h all squared. Put my f of x inside of here. Divided by h. Now, these guys, we've been doing guys like this all semester at this point, so let's just get through that. We expand this. Get the x squared root, subtract the x squared. There's a common h in the top, which I can factor out. Didn't take the limit yet, but the h's cancel at this point. So now I can take the limit as h is approaching 0, I can just plug in 0 now because I cancel the 1 in the denominator. And the answer is going to be 2x. So it turns out the derivative of the function x squared is 2x. And what you can think of that as, this is a formula for the slope of the tangent line at x. So I went through this whole process. I created I took that limit. So my function f prime is the function 2x. What you can think of as this is giving us a formula for the slope of a tangent line at any point. So basically, if I want to find the slope of my tangent line to any point of this function, I simply have to take 2 times that x value, and that will give me the slope of the tangent line. So the slope of the tangent line when x equals 1 is going to be 2. So a tangent line when x equals 7 is going to be 14, and so on and so forth. But we cared specifically about the point 2. So at x equals 2, this means that our f prime was actually 2 times 2, which is 4. And so what I would interpret that as, this is this slope of the tangent line at x equals 2. In other words, you can see what's happening here as a picture. if when your x value is 2, you see this function here at that point, and you draw a tangent line to that function at that point, that passes through that point. So you draw a straight line that passes through that point, such that if you zoom in, the line and the function will be very close together. Then it turns out the slope of that line would be equal to 4. There are many times where we're going to actually want to find the equation of the tangent line. How would I actually do that? How would I go about finding the equation of this line?
Plugging into the slope formula.
Well, I know the slope. We know m equals 4, so the slope for that line is 4, but what else do we need?
Y equals mx plus b.
Right, we need y equals mx plus b, but what would we need to get to that?
Some points.
We need a point. Okay, so we know the slope, we need to get a point. How do we get the point?
You look at the graph
Okay, and how do you determine the point here?
for the lines with the 2.
Come again?
You just plug into it.
Plug in 2, right? We care about at the point where x equals 2. At that point, x equals 2, we're on the function at some point, and that's the same point that the line is going to go through. So, when x equals 2, this means that your y value is going to be 2 squared, because the function is x squared. So I plug in into the function, and so that's 4. And so I know that 2 comma 4 is on the line. And so this means if I take y minus 4 equals 4x minus 2 is the equation of the tangent line. Right, or I could write it as just in y equals mx plus b form. That's 4x minus 8 plus 4, 4x minus 4 would be that equation. So if I look at the function x squared, I draw a tangent line at the point where x equals 2. Turns out the equation of that line will be this. The slope of that line will be 4. That slope can actually be interpreted as the rate of change of the function. Which means if I actually put units on the x and y axis, and I can talk about those. So if this is in terms of miles and hours, I know that at the point when x equals 2, we would have been traveling at 4 miles per hour, for example. Is one way we can interpret this, right? And that's me interpreting something on a curve. Something that we don't, it's not a straight line, but we can actually use a straight line to, yeah, did you have a question?
Yeah, so how would you, I guess, determine the slope if, like, we weren't given a point? Would you say it was, like, somewhere in the middle of, like, I don't know, 1 and 2 or somewhere in that line?
Well, the whole point of finding a derivative, it means that there is some point usually that you're concerned about, so you will kind of know what that is, usually. You could actually, the derivative, I erased it. The derivative in general has some nice properties, so if you actually look at this function by itself, the function 2x, knowing that's the derivative in general does give you some ideas that we'll talk about earlier. But in general, at a point, like I'll usually ask you about the point, or you'll know at the point that you want to do it. Yeah, there's a lot more to talk about derivatives. I really only told you about the basic definition here, but we're going to get a lot more complicated with it pretty soon. But so far, that's one way we can apply a derivative. We'll stop there for now. So it turns out if our function is x squared, our derivative is 2x, and that's a function that gives us the slope of the tangent line.
So
Yes?
it's only 2.2.